All right, let's jump right into this deep dive. Today we're exploring Andrew Ng's machine learning yearning, and it's full of great practical advice for machine learning projects.
Yeah, it's almost like having like a mentor sort of like walking you through all the decisions. That can really make or break a project. It helps you go beyond just theory and build ML systems that work in the real world.
Exactly, making sure everything just fits together, from picking the right data to how you evaluate your model. Speaking of data, machine learning yearning really emphasizes this idea that scale drives progress.
Right.
More data, bigger models. Is that really all there is to it?
Well, there is some truth to that for sure. Larger data sets and models, they often give you more performance, but it's not always that straightforward. Sometimes you end up with these diminishing returns or even run into unexpected challenges, so you can't just throw more resources at the problem and call it a day.
Okay, so when does scaling up not work? Do you have an example?
Sure. Let's say you're trying to build a system to identify different types of trees from images. It's tempting to just grab millions of tree images from the web and train a huge model on that. But what if all those images are, you know, trees in perfect light with
Hmm.
clear backgrounds? Then when your model sees a real tree with, shadows and clutter, it might completely fail.
Oh, okay. So it's not just the ANA data. It also has to reflect the messy real world.
Absolutely. And
Yeah.
this leads right into choosing the right development and test sets.
Right. And uses that example of the cat classification app. The model does amazing on a test set of high-res website images,
Hmm.
but then totally bombs when users upload blurry phone pics.
Yeah, it reminds me of a project I worked on early in my career, actually. It was to identify different aircraft from satellite images. We had this data set with super clear pictures, and our model was really accurate on the test set. But when we actually deployed it, the model struggled to classify aircraft in the grainy, low-resolution images from the real satellites.
It's like training for a marathon on a treadmill and then having to run through a jungle.
Ha, exactly. You have to make sure your dev and test sets match the data your model will see when it's out in the wild. Otherwise, you're going to have problems and potentially even project failure.
And I remember Anne being very clear about the dev and test sets needing to come from the same distribution. No mixing and matching.
Right, because it's tempting to, split your data by geographic region or by different sources, but that just makes things uncertain. You won't know if improvements on your dev set actually translate to the real world.
It's like studying for a test using notes from a different class. Might ace the practice questions, but then,
You'll be lost on exam day, yeah. The takeaway here is that having the right dev and test sets is essential for good evaluation and for making informed decisions throughout your project.
so once we've got our dev and test sets sorted, how do we actually go about evaluating our model? Ng talks a lot about having a single number evaluation metric. Why is that so important?
Choosing one metric is like setting a clear direction for your whole team. Everyone knows the goal, and that speeds up decision making, avoids those, endless debates about which model is better.
So instead of looking at precision and recall separately, you might just use the F1 score.
Exactly. Or you might have to define your own metric, one that's specific to your project. Like if you're building a wake word detection system, you really care about minimizing false negatives missing the wake word.
Yeah.
But you also don't want too many false positives where the system wakes up when no one said anything.
Right, so that custom metric captures the trade-off between those two types of errors. But I imagine it can be tough to get everyone on the same page and agree on that one perfect metric.
It can be, definitely. Clear communication is key, and involving stakeholders early on is important too. That way everyone understands what they're aiming for and what the trade-offs are with different metrics.
Okay, so we've got a clear metric now. How do we actually improve our model? Eng really emphasizes iterating quickly.
It's like building a house. You wouldn't spend forever perfecting the foundation before thinking about the walls. You build a basic structure first and then refine it based on, what works and what doesn't.
He uses that example of an anti-spam system. You start simple, see where it fails, and then iteratively fix those specific problems.
Right. And that's where error analysis comes in. By looking at what your model gets wrong, you can figure out where it's weak. And that tells you where to focus your efforts.
I love that story about the dog, great cat, blurry spreadsheet. Eng's a big fan of manual error analysis.
It's such a simple but effective technique. You go through, say, 100 misclassified examples and categorize them, and that quickly gives you a sense of the patterns and trends in your errors.
In that case, it turned out 43% of the errors were the model mistaking big cats for house cats. And then a whopping 61% were due to blurry images.
Exactly. And that kind of insight can completely shift the direction of your project. Instead of spending weeks trying to fix one type of error, you might realize it's actually not that big a deal compared to something else.
It's like spending hours cleaning the kitchen floor when the real mess is the overflowing garbage can.
Ha! Perfect analogy. It's all about finding the areas where your effort will make the biggest difference.
All this talk about errors leads us to the two main culprits in machine learning: bias and variance.
These are the two fundamental forces you're always battling in ML. Bias is about how well your model fits the training data. High bias means it's too simple, can't capture the patterns.
So it's like trying to fit a square peg into a round hole.
Right, and then variance is all about how much your model's performance changes when you train it on different data sets. High variance means your model is overfitting, too sensitive to the specific data it's seen.
It's like a student who aces the practice test but then totally bombs the real exam.
Exactly. Eng has this great example of a cat recognition model. Let's say it has 1% training error, but 11% dev error. That's a clear sign of high variance. It's not generalizing well.
So how do we figure out whether it's bias or variance that's causing us problems?
One of the first things I always look at are the learning curves.
Learning curves. Refresh my memory on those.
Sure. A learning curve is basically a plot of your model's error on the development set as you give it more and more training examples. It's a way to visualize how performance changes as you feed it more data.
So kind of like a map, making sure you're going in the right direction.
Yes. If the curve has flattened out, you know adding more data won't help. But if it's still going down, more data could make a big difference.
Interesting. So these learning curves can help you decide whether to focus on getting more data or try other ways to improve.
Exactly. They help guide your decision making. Now, along with looking at learning curves, it's also important to compare your model to another benchmark, human-level performance.
Oh, right. Eng talks about how comparing to human performance can give you valuable insights, especially in areas where humans excel, like image recognition.
Yes, exactly. Like having a master chef judge your cooking, they can point out areas where you can improve.
I love that. And this comparison can help you make decisions about your model. Like if your model keeps making mistakes that a human wouldn't, you might need to rethink your entire approach.
Right, or if it's already better than humans in some areas, maybe focus on the parts where humans still have the edge. So it's all about using human performance as a guide to set realistic goals and know what's possible.
And this ties into the idea of the Bayes error rate, right? The lowest possible error rate for given tasks.
Yes, exactly. Even if you're not aiming for human-level performance, knowing the Bayes error rate tells you how much room for improvement there is.
Helps you set those realistic expectations and avoid chasing impossible goals. Now, while we're talking about different approaches, let's talk about end-to-end learning. It seems like that's all the rage these days. Eng uses sentiment classification as an example,
Yeah.
figuring out if an online review is positive or negative.
Right. Traditionally, you'd build a pipeline. First identify important words and then analyze those to classify the sentiment.
But with end-to-end learning, you just throw the raw text at a neural network and let it figure everything out on its own.
That's the idea. It's like giving someone all the ingredients and saying, bake a cake, but without a recipe. You're relying on the model to learn everything directly from the data.
Sounds powerful, but I'm sure there are some downsides.
Well, one big challenge is that you usually need a ton of data for end-to-end learning to work. If you only have a limited data set, those hand-engineered features from the traditional approach might actually work better.
Eng talks about speech recognition, how the traditional approach involves breaking the audio into phones, those basic units of sound. But with end-to-end learning, you could just feed the raw audio to the model.
Exactly. But without enough data, that end-to-end model might not be able to learn the complex relationship between the audio and the text.
So it's a trade-off between simplicity and needing lots of data.
Yes. And sometimes end-to-end learning just isn't an option, like with autonomous driving.
Oh yeah, good point. It would be impossible to collect enough data to train an end-to-end self-driving system.
Wow.
All those sensor inputs and the corresponding driving actions. That's just too much.
And even if you could get all that data, there's no guarantee the model would handle new situations that it hasn't seen before.
The real world is way too unpredictable.
Exactly. So in cases like this, it's better to break down the task into smaller pieces like detecting objects, recognizing lanes, and planning the car's path.
And then each of those smaller modules can be trained more effectively using existing data and knowledge from those areas.
Exactly. You can build more specialized and robust systems that way.
So it seems like building a good machine learning system is about making smart choices based on the problem you're trying to solve.
Absolutely. Understanding the trade-offs, finding the right balance between simplicity, performance, and data.
Well, I think that's a great place to pause for a moment. We've already covered so much.
So yeah, sometimes it makes more sense to break down a big, complex task into smaller, more manageable pieces.
Right, like we were saying with that self-driving car, it's way easier to collect data for specific tasks like lane detection or pedestrian detection.
Yeah, exactly. Plus, you can use existing data and knowledge from those specific areas, like for object detection or image segmentation. There's already so much research out there, so many data sets.
Okay, that makes sense. But with all these different pieces working together, how do you make sure the whole system actually, works? It seems like it could get pretty complicated.
It can, for sure. And that's where error analysis by parts comes in. Instead of just looking at the errors for the whole system, we want to figure out which part is causing each specific mistake.
Oh, so it's kind of like a detective at a crime scene. You don't just look at the whole scene. You have to carefully examine each clue to figure out what happened.
That's a great way to think about it.
Huh.
Eng uses the example of a Siamese cat detector. It has two parts, one that detects cats and another that classifies the breed.
So let's say the system says an image doesn't have a Siamese cat, but it actually does. How do we use this error analysis by parts to find out what went wrong?
You'd look at each part separately. Did the cat detector even see a cat in the image? Or did it see the cat, but then the breed classifier got it wrong?
Ah, I see. So by isolating the problem to a specific part, you can then focus on improving that piece of the pipeline.
Exactly. And the book even has this cool trick to formally figure out which part is to blame for each error. You basically replace the output of one part with a perfect output, either by doing it manually or using another really accurate model.
Okay, walk me through that. How would that work with the Siamese cat detector?
Let's say we give the breed classifier a perfectly cropped picture of the cat, so we know it's definitely seeing the cat. If it still gets the breed wrong, then we know the problem is with the breed classifier itself. But if it correctly says Siamese cat, then the original mistake must have been because the cat detector didn't give the classifier a good enough image to work with.
Oh, that's really clever. It's like giving the suspect a lie detector test.
Huh. It's a super helpful way to find the weakest link and know where to focus your energy. And it works really well with what we were talking about earlier, comparing your model to human performance. If one part of your system is consistently making errors that a human wouldn't, that's a big red flag.
Yeah, that makes sense.
Mhm.
So we've talked about breaking down tasks into pipelines and analyzing errors at each step. But what if all the individual parts seem to be doing well, maybe even as good as a human, but the whole system still isn't performing as well as it should be?
That's a great question, and it suggests there might be something wrong with the way the pipeline itself is designed. It's possible that the individual parts, even though they're doing well on their own, aren't giving the right kind of information to the next stage in the pipeline.
So it's like having a bunch of amazing musicians who can all play their instruments perfectly, but they sound terrible when they play together because the conductor is messing up.
Uh-huh, exactly. Aang brings back the self-driving car example to explain this. Let's say the car detection and pedestrian detection are both working perfectly, but the path planning module is still making bad decisions, leading to unsafe driving.
So it's not that the individual parts are broken, but that the information they're sharing isn't enough for the next step to make the right call.
Right. It could be that the path planning module needs more information about the surroundings, like maybe it needs to know about lane markings or the speed and direction of other cars.
So you might need to redesign the pipeline, maybe add a lane detection module, or change how the different parts talk to each other.
That's it. You need to make sure each part has the information it needs to do its job and contribute to the overall goal of the system.
Okay, so it's not enough to just have good individual components. You need to think carefully about how they work together.
Absolutely. And this brings up another important point Aang makes. Sometimes there's a mismatch between the data you use to train your model and the data it sees in the real world.
Right, like that cat classification example. You might train your model on high-quality images from the internet, but then users are uploading blurry photos from their phones.
Exactly. And that mismatch can cause problems. The book gives some good advice on what to do about it.
Tell me more. How do you deal with that?
Well, first, you need to look closely at the errors your model makes on your development set. See if you can spot any patterns that might point to differences between your training data and the real-world data.
So, like in that cat example, you might notice that the model keeps misclassifying blurry pictures or photos with bad lighting.
That's right. And once you know what the differences are, you can try to make your training data more realistic.
So you might go find more blurry cat pictures or use data augmentation to make your existing images blurrier.
Exactly. Data augmentation can be really helpful in situations like this. You can also adjust the weighting of your training data. Basically, tell your model to pay more attention to certain examples.
Like saying, okay, model, these blurry pictures are important, so learn from them extra carefully.
Haha, good way to put it. The main point is to train your model on data that reflects the challenges it will face in the real world.
Makes sense. I'm starting to see that building a good machine learning system isn't just about the algorithms. It's about making strategic decisions every step of the way, from the data you collect to how you design your pipeline and analyze errors.
You got it. Machine learning yearning does a fantastic job of highlighting these strategic aspects, giving you practical guidance for navigating real-world ML projects.
And this is where we'll pick up in the next part. All right, we're back for the last part of our deep dive into machine learning yearning. We've covered so much already, but Andrew Yang still has more to teach us.
Yeah, what I really like about this book is that it doesn't sugarcoat things. Aang really digs into those tricky situations you run into in real ML projects. Like what happens when your data is, inconsistent?
Inconsistent. What do you mean by that? Can you give me an example?
Sure. Let's say you're trying to predict housing prices. You've got data on apartments in New York City where, prices are sky high. Then you find another data set with houses in, say, Detroit, where prices are way lower. What do? Just combine everything into one big data set.
I don't know about that. It feels like those two markets would be totally different.
You're right to be hesitant. The book says the key question is whether the relationship between the features and the target variable, in this case the housing price, is consistent across both data sets. Can you use the same features to accurately predict the price of a house, whether it's a fancy Manhattan apartment or a modest home in Detroit?
So it's not just about the prices being different, but whether the things that determine those prices are the same in both places.
Exactly. If those underlying relationships are different, just combining the data sets could create a model that doesn't work well for either one. You might be better off keeping them separate or adjusting your model to account for those regional differences.
So you really need to understand the nuances of your data and not make assumptions about how different data sets relate to each other.
Absolutely. And even if you do decide to combine them, you might need to think about weighting the data. Give more importance to examples from a particular data set, especially if it better reflects the real-world data you're interested in.
That makes sense. Now, I remember being fascinated by Nang's discussion of debugging inference algorithms. It was a new concept for me.
Oh yeah, that's a good one. It shows how even the algorithms we use for inference, not just the models themselves, can cause errors.
He talks about speech recognition systems that use beam search to find the most likely transcript for an audio clip.
Right. The thing with beam search is it's a powerful algorithm, but it's not guaranteed to find the absolute best solution every time. It's a heuristic method, meaning it explores a limited set of possibilities to find a good solution quickly. So even if your model is good at scoring different transcripts, the beam search algorithm itself might miss the best one.
So how do you know if it's the search algorithm that's messing up, or if it's the model's scoring function? Seems tricky to separate those two.
That's where the optimization verification test comes in. It's a smart way to figure out which one is the problem. The idea is to compare the score of the correct transcript, which you already know, with the score of the transcript produced by the system using beam search.
Okay, so you're basically checking if the search algorithm is finding the highest scoring transcript according to your model.
Exactly. If the correct transcript has a higher score than the one the system gives you, then you know the beam search algorithm messed up. It didn't find the best solution, even though your model could have.
And if the wrong transcript actually have a higher score, then the problem is with your scoring function. It's not accurately evaluating the different transcripts.
Precisely. This test is really useful for pinpointing the source of errors in systems that use optimization. It helps you focus your debugging efforts in the right place.
That's so clever. I bet you could use that for more than just speech recognition, too.
You're absolutely right. The optimization verification test can be used for any system that uses an optimization algorithm, like reinforcement learning or machine translation.
Before we finish up, I want to touch on one last point that really stuck with me. Designing ML pipelines based on data availability and task simplicity.
Yeah, that's a crucial point. It goes back to our conversation about end-to-end learning and when it's not the best option.
Right. Sometimes you just can't train an end-to-end system because you don't have enough data, or the task is too complicated to learn all at once, like autonomous driving, for example.
Perfect example. Trying to collect enough data to train an end-to-end self-driving system would be a total nightmare. But we've got mountains of data for specific tasks like lane detection or object recognition.
And by breaking down the complex task of self-driving into these smaller, simpler subtasks, we can use the data and expertise that already exists for those areas.
Exactly. It's much more practical and often works better. And as we discussed earlier, it makes it easier to analyze and debug individual components.
So it's a win-win. You can leverage existing knowledge, and you end up with a system that's easier to understand and improve.
Couldn't agree more. This really highlights a key takeaway from machine learning yearning. Building successful ML systems is all about making strategic decisions at every stage. It's not just about knowing the algorithms, it's about understanding your data, picking the right tools, and constantly learning and improving.
Well said. So, to sum it all up, what are the main things our listeners should remember from machine learning yearning? What can they start using in their own ML projects today?
I think the biggest thing is don't underestimate the importance of thinking strategically. It's not just about building models. It's about making smart choices at every step, from collecting data to analyzing errors. Think about your goals, your resources, and the specific challenges you're facing.
And don't get stuck trying to make everything perfect from the start. Embrace the idea of iterating quickly. Build a single system, see what goes wrong, and then fix those specific problems.
Definitely. And don't be afraid to really dive into manual error analysis. It's super helpful for understanding how your model behaves and finding the best ways to improve it.
And remember that your training data isn't always a perfect reflection of the real world. Be aware of those potential mismatches and find ways to make your training data more realistic so your model will actually work when you deploy it.
All great points. And I'd add one more. Always keep learning. Machine learning is constantly changing, and there's always something new to learn. Stay curious.
Absolutely. Machine learning yearning is a fantastic starting point. It's packed with practical advice and real-world insights that can help anyone build better, more robust ML systems.
Yeah, it's a must-read for anyone working in machine learning, no matter how much experience they have.
Well, that brings us to the end of this episode of The Deep Dive.
Yeah.
We hope you've enjoyed exploring machine learning yearning with us. Now go out there and build some amazing ML systems.